Okay, hello everyone. My name is Yunpeng. So I'm a software engineer at Uber. I work on building and maintaining Uber compute platform. So here today, I'm going to talk about the best practices of using Mesos at Uber. So before I start, I want to give a quick thank to Mesosphere and KBSYS for having me here. So since this is my first time in Korea, and also this is my second time to give a guest talk at a conference that hosted by Mesosphere. I feel honored and excited, so hopefully the information I'm going to share will be helpful to you guys. Okay, let's start. Okay. First of all, we're going to talk about why Mesos at Uber. So let's roll the time machine back to 2016. So back to 2016, Uber already had an in-house built, customized end-to-end deployment platform. So which means Uber actually handles the applications from their source code to build, to deploy, to actually manage their online services, all by this in-house built platform. Speaking of the scalability, back to 2016, Uber already had thousands of different kinds of microservices. So every single of these services can scale from like 10 instances to up to like a few thousand instances. Speaking of the hosts, Uber already have thousands of physical hosts under our compute platform. But there's a problem. So the in-house built customized deployment platform actually are all static, which means everything is static. We don't have auto scheduling, we don't have auto balancing. So you can imagine it's basically all the steps from, for example, you're adding a host to the platform, you're assigning a host to different services, or there's something goes wrong with a physical host, you take that out, you rebalancing the host assigned to different services. All these steps are not supported by the scheduler inside this framework. They're all static. But there's also an upside here. So back to 2016, most of the services that already running in Uber, they're already being containerized. So if you're looking at all these bullet points we're putting on the slides, you'll be actually realize that, okay, Mesos back to the time would be a perfect solution for us because essentially Mesos gonna support our needs for scalability, and Mesos will bring in the required features for auto scheduling. And also, if you're looking at the condition in our service instances, because they are already containerized, that makes the migration from the pre-existing customized platform to the new Mesos-based platform much more easier. Okay, so I think we can all agree that back to 2016, Mesos is the perfect solution for us. Then let's talk about how we actually adopt Mesos. So here, interestingly, instead of actually replacing the whole end-to-end stack Uber already built in-house with, for example, some pre-assembled solution like DCOS, we actually directly integrate with Mesos with our customized deployment platform, which consists of a Docker-based build pipeline, which supports different kinds of languages, you name it, like Python, Java, Node, Go, etc. And also, it consists of an UI which powered by a middle tier. This middle tier can actually abstract the deployment and environment modules for users to actually can easily deploy and manage their instances. And also the last one, so our in-house built customized platform also consists of a cross-zone, cross-cluster orchestration layer. The second thing is, so inside Uber, we actually use Apache Aurora as our stateless workload scheduler. So Apache Aurora is a Java-based open source project which initiated by Twitter. So back to that time, Apache Aurora already widely adopted by Twitter as a critical piece of their compute platform. And their compute platform was actually beyond the scalability, beyond the scale of Uber's compute platform back to 2016. So which means to us, we think Apache Aurora is a very solid decision that we can make to take as part of our critical piece inside our compute platform. Okay, the last point is also interesting, so I want to emphasize here is because inside Uber, we actually co-located multiple schedulers on top of a single Mesos cluster. This situation got changed later in the game, but you will see a lot of downside and upside related to this decision I'm going to talk about later in the slides. Okay, so to summarize all those bullet points onto this top-level architecture diagram, which represents the compute platform stack at Uber. So essentially, this stack actually not only including the how we manage stateless workload at Uber, it also includes how we actually manage our stateful and batch workloads. But right here, I want everyone to just focus on this list for now. So, so if you're looking at the left top corner of this diagram, you will see that small blue block actually represents the in-house built, customized deployment platform I mentioned before. So that's essentially the component act as the integration gateway for us to plug in the Mesos Aurora stack. So basically, we integrate Aurora APIs with that component, and Aurora sits on top of Mesos master. And you guys are familiar with the underneath Mesos architectures. But there's another thing I want to talk. If you're looking at the agent, represents the stateless workloads. So essentially, we use Docker as our container runtime to power the stateless workload. And we also use the Thermos executor, which provided by Aurora, to actually execute those tasks on the agent. So we already overlooked how Uber actually adopted Mesos. Let's talk about the benefits. So it's quite surprising. After we adopting Mesos, so suddenly all the problems we mentioned in the previous slides, they are solved. So which means essentially Mesos gave us a very good scalability to scaling our compute platform horizontally. And also, because the natural two-layer scheduling support in Mesos, we actually have a more efficient scheduling story compared with our previous pretty static deployment platform. And another interesting point here, I think, is hidden behind the scene is to adopt Mesos actually helped us to reduce the operation overhead. If you're thinking about how I described that we manage the instances underneath our classic static compute platforms. So basically, all those nitty-gritty instance management are either done by partially automated scripts or just by human beings, which is pretty operational heavy. Another interesting point is because prior to adopting Mesos, Uber already have an end-to-end build deployment platform. So which means we want to actually leverage that platform. Then adopting Mesos actually made it pretty easy for us to integrate our existing Docker-based build system with the new compute platform. So now what? We're already running majority of our stateless workload on top of the new compute platform based on Mesos. Then what's next? So it's naturally to think about expanding the use cases of Mesos inside Uber. Then you see there's a bunch of different kinds of workloads we can try to explore. There are batch workloads, there are stateful workloads, there are daemon set workloads, and et cetera. So let's talk about these use cases. The first one, stateful workload. The stateful workload we're actually running on Mesos is Cassandra. So if you're looking at the right side of the slides, this diagram actually represents a brief architecture of how we spawn up Cassandra workload on top of Mesos. So at the very top, we have a component called Cassandra Mesos Scheduler. This essentially is a stateless workload managed by Aurora. And this Cassandra Mesos Scheduler actually takes charge of spawning the Cassandra cluster scheduler, which essentially is the stateful workload scheduler on top of Mesos. And underneath, on the agent side, our Uber's Cassandra team actually developed their own cluster or node executor to actually manage the containerized Cassandra node on each Mesos agent. And there's several interesting hitting points behind this architecture graph. So the first one is the Cassandra team took a decision to actually spawn up a new or separate Mesos framework per Cassandra cluster. And this decision actually also leading to the second point is because you can imagine inside each Mesos cluster Uber operates, we often support multiple Cassandra clusters. In that case, we're going to have multiple Cassandra frameworks on top of the Mesos cluster. And the third part is basically on the data persistence between process restart or host reboot. We're actually utilizing Mesos persistent volume to achieve that. Okay, second extended use cases. This is batch workload. This is more interesting because I think at late of last year, Uber finally open sourced our in-house unified scheduler, which is called Peloton. So Peloton is an open source project based on Golang. And we started the development of Peloton as a batch scheduler on top of Mesos, even though the motivation of this project was to build a unified schedulers. So after we successfully onboard batch workload on top of Mesos through this new Peloton scheduler, we're starting to expanding the use cases to support stateful and stateless workloads through Peloton as well. So there are two key features Peloton supports I want to emphasize. The first one is Peloton actually supports hierarchical resource pool, so which means it actually enables you to manage your quota among a lot of different teams, more flexible, and give you a little bit power to actually construct different kinds of quota structures you need. The second thing is the elastic resource quota, which essentially you're going to gain a lot by leveraging this elastic resource quota to increase your cluster utilization efficiency. Let's take a look architecture graph of Peloton. So this is a graph I stole from my awesome co-workers who actually built this system. So it's a little bit overkill. There's a lot of details, implementation details inside this project, but let me try to abstract some key points here. So the Peloton team actually divides the scheduling functionalities into 4 modulars. It reflects to 4 different components inside this Peloton project. They are job manager, resource manager, host manager, and a placement engine. And Peloton also uses Cassandra as the persistent storage powers its backend. And Peloton used Zookeeper as a common solution for leader elections to achieve high availability. Okay, so far we've all talking about good things, but you guys all know that there's no perfect projects, there's no perfect technology in the world. So you're always gonna run into a bump up of issues along the road. So I summarized certain limitations we experienced during the journey, but so to be clear, this is not a limitation on Mesos particular. This is more like the limitations on the end-to-end solution, how Uber adopted Mesos so far. So the first one is framework scalability limits. So interestingly, so far we haven't run into any scalability issues with Mesos itself, but we have been hitting by the scheduler scalability limitations several times. The second thing is common problems, I believe, for people who build their compute platforms based on this kind of modernized architecture of products like Mesos. Because, so currently we have a very high resource allocation in the cluster, but the actual resource utilization rate is pretty low. So this is quite a big issue right now we are facing and trying to fight with. Next one, yes, so Uber compute platform trying to actually introduce in-place upgrade. There are 2 particular reasons I can think of. So the first one is there are a bunch of stateless services. They have special requirements, like they need sticky cache. They need stickiness with their local cache, or they utilize static IP in a way. So all this kind of features built in those services, we thought in-place upgrade would be a solution for them. The second thing here is because I mentioned before, we run into the scalability problem with the frameworks. So we actually thinking in-place upgrade would actually help us to reduce the churn rates inside the cluster, which can potentially enable us to scale the frameworks a little bit more. Next one is related to how we support stateful workloads like Cassandra on top of Mesos. So because we actually utilize Mesos persistent volume as the way how we actually support those stateful workloads, there were some limitations as of last year when we actually still helping them actively. So we ran into certain limitations, and we have to provide certain workarounds and actual efforts to support those stateful workloads properly. Next one, schedulers does not adopt Mesos maintenance primitives. So this is something related to the operation side. So imagine you are actually operating Mesos cluster at scale. You would rather directly talking with Mesos instead of talking with individual frameworks on top of Mesos, if that's possible. But the fact is, both the stateless scheduler we're using, like Aurora, as well as the stateful workload scheduler we're using, like the Cassandra team's built in-house schedulers, neither of them support Mesos maintenance primitives, so which creates actual workload on the SRE side to try to operate the cluster. The last one is a minor one. So along the road, when we're scaling up our Mesos clusters, we realized that the Mesos UI actually had a performance degradation when the cluster goes beyond certain size. And also, certain operations on the UI might be very resource consuming. It might actually impact your cluster performance at the peak time. Okay. After the limitations, there's also some valuable lessons we have learned along the journey. So the first one is manage agent configurations at scale is quite challenging to us. So there are two things I wanted to mention here. The first thing is, if you can imagine you are operating many Mesos clusters in your production environments. So on these different clusters, you might actually run different kinds of workloads. So it's very likely you're going to have different combinations of Mesos agent configurations. You need to maintain and update on those clusters separately, which makes the problem pretty tricky. The second thing is, if I remember correctly, I think prior to Mesos major release 1.6, there were certain Mesos agent configurations. They are not really restart compatible, which means if you want to change those configurations on the Mesos agent host, so essentially you have to drain all the running workloads off the agents and kill the agent's process, let it re-register as a new agent with a new UUID. In that way, the agent wouldn't really fail at the recovery checkpoints. So if you can imagine, if we need to roll out certain configurations across the whole fleet, this essentially means we need to drain every single running containers in the cluster. Essentially means we need to restart and reschedule every single instances we run or we manage on the Mesos cluster. But the good news is I think the Mesos team did a great job to actually address these concerns. They introduced a flag called reconfiguration policy after that major release, which solves us pain in the ass. Okay. Next one. Yeah, so that's also an interesting problem because at the beginning, when we start to support stateful workloads in Uber, we actually support stateful workloads as Cassandra on the same Mesos cluster with the other major stateless services we run. So essentially means, if you guys can recall that we mentioned that for each Cassandra cluster, we actually spawn up a new Mesos framework for that. Essentially means, in a common basis, Uber usually have more than 50 Cassandra clusters per Mesos cluster, which means essentially you're going to have more than 50 Mesos frameworks running on top of the same Mesos master quorum. So the offer contention might be very tricky when you have so many frameworks co-located together. So it took us quite a while to figure out a reasonable solution to deal with it, including like tuning different kinds of Mesos master configurations, framework configurations, as well as changing the attributes on the agent side, trying to lock and reserve certain agents' offers for a specific framework. Next one is, yeah, that's a hard lesson we learned from Blood. It's basically, co-location of stateless and the stateful workloads in the same cluster at scale might not be a good idea right now. So unless you really have confidence to manage that properly, then probably try to avoid it at the beginning. Next one, we need to be careful when we're enabling oversubscription. So essentially, oversubscription is a feature that Mesos enables us to be able to provide two types of offers, such as non-revocable offers versus revocable offers, which means from a technical perspective, you can imagine for each Mesos agent in your cluster, typically if a physical host would have 24 cores, actually Mesos is advertising more than that to the framework. So, and that means we can try to increase the cluster utilization by over-advertising more resources than it actually has. But at the beginning, we thought this is more like a free resources we can give to the customers, we can give to the clusters. But it turns out this free resource is not really free because there are a lot of tricky things you need to deal with it. For example, there are dynamic resource estimation you need to do on the agent side locally. There are graceful shutdown of each running instances you also need to deal with on the agent side. There's also like extra chain rates you introduce in the cluster. So those are like tricky problems. You need to be careful when you're thinking of actually leverage this kind of features to increase your cluster utilization potentially. Yeah, and the next one is more like a common sense. I think everyone works on the infra side of your like compute software world. You wouldn't know this, like migrations always took longer than expected. So at the beginning, we were planning to migrate all major workloads of our previous static deployment platform to the new Mesos-based compute platform in a year. But it ends up like finish everything in almost 2 years. So I think as of early last year, we finally killed the previous platform and now runs all the stateless workloads on the new platform. The last one is also operation automation is essential at scale. This is more like a common sense, but we would want to emphasize it here because even though Mesos, like Aurora or like DCOS, they are all like modernized infrastructure support, but essentially you still need to spend quite a lot of time on building up automations around your operation if you're really operating those softwares at scale. Okay. The last part of my presentation, I want to focus on the operation automation a little bit. So there's a product we built inside Uber called CLM. It stands for Cluster Lifecycle Management. So this CLM framework actually is a centralized automation for host and cluster management at scale. So it has certain key features. It's a config-based Go state it leverages a config-based Go state to build and shape clusters and also including provision hosts. So it also manages agent versions and configurations based on configuration, Go state configurations. And also it provides a common host maintenance like a kernel upgrade. Yeah, it also detects and remediates host issues with configurable escalations. So the interfaces with scheduling layer to perform ops safely, also respect the service SLA is also a built-in feature in this product. Okay, this is more like a simplified architecture diagram. So here you can clearly see there are 3 major modules which consist of this CLM product. The first part is the issue generation part. The second one is issue dispatch. The third one is issue remediation. So the general workflow looks like we have a host inspector agents running as a daemon on each single physical host. It's periodically collecting the actual state of that host and reporting that state back to the issue generation modules. Then the issue generation modules run through various of different kinds of validations based on the pre-configured cluster Go state. And if there's any divergence, it creates an issue. And this issue got ingested into the issue dispatcher workflow modules. The issue dispatcher module essentially do a bunch of configuration mappings, mapping those specific issue into a workflow object, and essentially pass down that workflow object to the issue remediation module. This issue remediation module essentially takes the charge of actual running the workflow on the local host to fix the issue. And also there's a feedback loop. So essentially, after the issue got remediated, the host inspector, since it's periodically collecting the actual state, it will try to report back to the issue generation part, seeing if the issue is resolved or not. So this is just a typical Go state-based automation system which adopts the common software controller model. Okay, I'm going to talk about those 3 major modules individually a little bit. So the first one is the issue generation module. So here, inside Uber, we have an in-house product called Grill. So this product is actually a graph-based aggregation platform for collecting and aggregating current state of the entire Uber infrastructure. So the benefits of using that Grill product is actually it's flexible and it's decentralized model for collecting and gathering states of the world. So which means we actually enables various of different providers to supply infra data and create issues for CLM to remediate. So give certain examples, like we have Nagios-based host issues. We have the agent version mismatch, which powered by Go state. We also have cluster composition diverge issues, which also powered by Go state. So I will touch on that a little bit. So what that means is basically, for example, from a cluster maintainer or operator perspective, what you essentially need to do is you just need to write a YAML config for your cluster. Here you specify how many hosts or agents you need for this cluster. And once this configuration gets committed into GitHub, so CLM actually will try to interpret that cluster config and compare with the actual state of the cluster. If there's any divergence between the actual agents running in the cluster versus the declared Go state, it will try to either scale down or scale up the cluster by provisioning more agents or decommissioning existing agents. Next part is the issue dispatch module. So here, for the issue dispatch module, we actually have a central process to detect and process issues. So we schedule and track workflows on a per cluster perspective. We also do locking on hosts or clusters to avoid contentions. This central dispatching process also applies priorities to address most urgent issues first. And we'll also apply escalation policies when workflow fails. Imagine you have a host unpinnable issues, for example. Then the first thing you're probably going to try is just simply reboot the host. Everything does it, right? Everyone does it. So, but it might not solve the problem all the time. So after you rebooting this host several times, you might try to say, rebooting doesn't really work, so let me try to reprovision the host. So this logic is actually being moduled as an escalation policy inside the product. The last one is we also apply relimiting to avoid impacting services SLA and the cluster health. So this means, for example, you might have a certain number of agents. They might either have disk failures or have have non-critical memory errors. You might detect those errors, but it's not necessary to maintain the host because some of the instances might still running fine on the host, right? In that case, you wanted to actually check the whole state of the cluster to make sure it's safe to pull out those non-critical hosts for maintenance instead of you suddenly destroy a large portion of your cluster capacity, then cause a capacity crunch on your cluster. Okay, the last module, the remediation part. So the remediation part actually runs workflows consisted of a decision tree to run specific activities and handle various of different cases. The second part is the activities inside the workflow actually executes one atomic operation on a host in the cluster. So there's also an open source project called Cadence, Uber built in-house. It's basically a distributed workflow management service. What it can do is essentially it can actually keep tracking of workflow state and dynamically assign to workers. It can also preserve workload state and reschedules if worker goes down. Basically, it's fault tolerant. And the actual worker services are owned by CLM, so which actually gives us the flexibility to scale horizontally to handle different kinds of workloads. Okay, after talking about each individual modules, let's just give a more detailed overview of the architecture again to help you understand how the entire data flow looks like. So again, it's the same host inspector agents running on every single physical host, collecting the host actual state periodically, and it ingests that host actual state into something we call Go state validators. So this Go state validator is actually reading the host/cluster Go state from our Go state storage. And if there's any divergence between the host actual state versus the Go state, it generates the issues and pushes it into the issues into something called issue cache. And this issue cache also helps to ingest these issues into the centralized issue dispatcher. And this issue dispatcher essentially handles the logic to translate the issues or mapping the issues based on configuration to the actual workflow object. And then the dispatcher dispatches the workflow object into the workflow engine. The workflow engine essentially executes the workflows and remediate issues on the local host. And as a feedback loop, the host inspector trying to reevaluate the actual state of the host. just by looking at those results, you might not really get a concrete picture of what's the benefits. So we're trying to summarize the benefits into just 3 big numbers. So the first one is just by onboarding to that automation framework, we were able to actually reduce our fleet management workload by 90%. So this number is simply measured by the on-call alerts our on-call engineer receives daily, and they need to triage. The second number is engineers involved in the fleet management reduced by 70%. This is also simply managed by the number of engineers on the team who needs to actually handle the fleet management work. And even further, so even if the engineers who still involved in the fleet management work, it's not a pain in the ass anymore. The last number is also interesting on the other side. So while we are reducing certain workloads on managing the fleet, meanwhile, we also scale up Uber compute platform fleet size by 200%. So basically means essentially scale up to 300%. It's a year-over-year calculation. Okay, that's pretty much ends up my presentation today. At the last slides, I wanted to give a sort of a summary, but it's not really a summary. It's more like certain bullet points I try to emphasize again. So the first one is, if you are considering using different kinds of frameworks on the raw Mesos, so you need to be aware of the scheduler framework scalability limits based on your specific use cases to make a wise choice. The second one is, I want to just try to emphasize again because we really learned this as a hard lesson. So try to avoid co-location of stateful and stateless workloads at the beginning, unless you have to, especially when you're operating a cluster at scale. The third one, the cluster utilization efficiency is very important at scale because essentially that's the key factor impacts your cost, basically. There's various of technologies you can think of trying to leverage. There's oversubscription supported by Mesos. There's a batch and the stateless workload co-location you can think of, but just be careful when you're actually trying to leverage those technologies. The last one is summarize the last part of my presentation is basically build up your operation automation based on ghosted. We, at least at this point, we think that's the right solution to go with. So this ends my presentation. Thank you.
네, 혹시 리우 윤팽님께 궁금한 점 있으신 분 계실까요? 네, 마이크 전달해 주시고요.
아까 클러스터 노드가 어느 정도 커졌을 때 UI가 로드가 되게 높아진다고 말씀하셨는데 어느 정도 커졌을 때 UI 로드가 높아진다는지 좀 궁금합니다.
I assume you're referring to the scheduler scalability limits there, right? So unfortunately, I cannot talk about the actual numbers. So because anything that's related to the actual production numbers not on the slides, unfortunately, I don't have the authority to share it. But in general, I can talk about, so definitely when you go beyond the 5K nodes with this specific stateless workload scheduler as Aurora, and if you're actually co-locating stateful workloads with your stateless workloads together, and you run multiple frameworks on top of your Mesos cluster, you're definitely going to hit some issues. Sorry, I couldn't really give a number, but in general, that's the situation. That's the first case we ran into.
네, 답변이 되셨나요? 네, 다행입니다. 네, 혹시 또 궁금한 점 있으신 분 계시면 손 들어 주십시오.
예, 저도 한국말로 하겠습니다.
네, 편하게 한국어로 질문하셔도 됩니다. 네.
혹시 그 메소스를 도입하기 전에 그 비슷한 솔루션을 검토를 해보셨을 거라고 생각이 되는데, 뭐 제가 알기로는 뭐 레드햇의 오픈시프트나 뭐 클라우드 파운드리 뭐 그런 게 있는 것 같은데, 그것들과 비교해봤을 때 메소스의 큰 뭐 장점이라든가 왜 메소스를 선택하셨는지 좀 궁금합니다.
Yeah, definitely. There are, even though I joined the team after that decision being made, but I know some of the historical stories. So One very simple reason that we have to go with Mesos, and Mesos is definitely the perfect choice, is speaking of the scalability. The scale Uber is already at back to 2016, and Mesos is the best solution that provides the scalability. I can make a simple comparison. I think back to 2016, if you compare Mesos with Kubernetes, Kubernetes is definitely not compatible. So speaking of the scalability. And the second factor is I actually forgot to thank Mesosphere teams. So we actually had a very good collaboration relationship with both Mesosphere as a company as well as the open source Mesos communities. So our engineers actually meet on site quite frequently, and they actually address our concerns quite prompt. So that's like more like a fact after the decision, but it's also a good thing to mention.
네, 좋습니다. 또 질문 있으신 분 계실까요?
You mentioned oversubscribing and underutilization of the cluster resources. Have you sorted out a best practice for recommending to the teams on them? And on oversubscribing, I mean, what's your approach to that? I mean, I haven't personally decided if that's a feature or a bug.
Unfortunately, we don't really have a fancy story to sell at this point, but I can tell a little bit what we have tried. We have tried to enable oversubscription as a Mesos integrated module. And what we are essentially doing to abstract the technical concepts is basically we just over-advertising the actual core resources on every single agent. And we're trying to classify the stateless workloads running inside Uber by severities. Because by oversubscription, we naturally actually divided the offer types, the Mesos offer types into two types. One is non-revocable types, the other is revocable offers. So which means non-revocable offer, which means this offer is reserved for you, or this amount of resource is reserved for your workloads. Which means unless you yourself take the decision to kill the instance, then this offer wouldn't be taken from you. The other one is coming from the oversubscribed resources, which called revocable offers. This offers means essentially these offers are temporarily allocated to you because even though they are reserved by other applications, but they are currently not utilizing it. But whenever those applications running with, for example, running with unexpected high loads, they start to utilize this resource, then you have to give up. Essentially, Mesos agent will make a local decision. If the agents go hot, it will just kill those non-revocable offers without negotiation. So by leveraging these features, we essentially we successfully avoid to scale up the clusters in certain circumstances. But as I mentioned, there are a bunch of issues related to that approach. Unfortunately, the way how we implement those dynamic resource estimation has implementation issues, and also because of the scheduler framework, the framework scheduler scalability limitations, because this oversubscription introduced local queues and introduced extra churn rates in the cluster, so which means we also hating our framework performance a little bit. So far we don't have golden solution for you. Sorry.
So you talked about the problem that you have very high allocation in the cluster, high allocation of resources, but still low utilization. We have a similar problem, and we put in a lot of effort to go through everything and then reduce the resources for individual services. So maybe a solution for this might be I can still have a third priority wish to Mesosphere from yesterday that I didn't have a third point. That my most important feature would be. The third one would be maybe to have more insight, more transparency on utilization, maybe even get suggestions on how to change allocation for services and workloads. I think that would be really helpful and would make us spend less time on going through hundreds of services.
네. 혹시 또 질문 있으신 분 계실까요? 네, 마이크 전달해 주시고요.
네, 아까 그 스테이트리스랑 스테이트풀 워크로드를 한 클러스터 내에 같이 넣는 거에 대해서 좀 어려움이 있었다고 좀 강조를 하셨는데 그거에 대한 좀 자세한 얘기랑 그럼 우버에서는 나중에 그거를 어떻게 해결을 했었는지 그거를 좀 알고 싶습니다.
Yeah, so I think I actually mentioned, but I didn't really directly pointing out that was the issue. So when you co-locating stateful workloads together with stateful workloads at scale, one obvious problem is on the operation side. So for example, Uber is not really using DCOS as ensemble solutions to build up this platform as a service, but because we integrate with the open source Mesos in a raw way, so which means we have to build all those operation solutions by ourselves. So imagine when you're operating a host only runs stateless services, which means you can kill that host at any time. Any other host can be the replacement, right? But imagine if this host actually runs stateful workloads, like a Cassandra node there. Essentially, you can kill it, but you have to be careful because if, for example, you are killing two instances together, two hosts together, those two hosts happen to run replicas for the same cluster, Cassandra cluster, essentially you are affecting that cluster's SLA or availability. So that's a major difference between, in operations, between you operating different kinds of workloads. The second thing is related to the offer contention between among frameworks running on top of the same Mesos cluster. So that was also a pain for us. It took us quite a while to actually have a viable solution to eliminate certain downsides of it. So the actual solution we deal with it is not, it's just to not deal with the issue. We essentially end up with just separate them into different clusters. That's why also just a personal opinion, I would suggest if it's not necessary, if we really run both workloads at scale, maybe better to think of don't co-locate them on the same cluster unless you have to.
네, 답변이 충분히 되셨나요? 좋습니다. 또 질문 있으신 분 계실까요?
So why did you build your own goal state config management tool and not build upon something like Ansible? I mean, we kind of did the same thing with DCOS deploy, but still interested.
Good question. So I think, so again, I'm not the best person to speak of the decisions made prior that, before I joined in the team, but I could imagine one of the reasons at the beginning when Uber decided to introduce Mesos into the company, but we didn't really go with DCOS. You could imagine that at 2016, Uber already have end-to-end solutions built in-house to take care of all the deployment platforms responsibility. Then introduce DCOS basically means you need to suddenly integrate or redo a lot of components inside that platform and make it work with DCOS, which as a company as Uber might not be a necessary solution to go at the beginning. And after we actually spent 2 years to deal with the open source Mesos, we have all the ecosystem built in-house. And also there are like, certain infrastructure that specific or unique to Uber's infrastructures that you have to take consideration when you build your automation solutions. So all those things actually ends up with building our own ghost-based configuration management system.
Good. 또 질문 있으실까요? 네.
Simple question. When you compose automation, what kind of tools or platform did you use?
So the automation framework we built is purely from scratch. It's a Golang-based framework. And we does, as we mentioned in the individual components details, we do integrate with certain technologies that Uber currently operates and support. For example, the graph-based cache system, which provides you the aggregated view of your whole infrastructure, which also gives you the flexibility of taking source data from different kinds of providers and essentially give you a quite easy read accessibility. The other one we use is called Cadence. It's an open source project, so you can actually look online. It's a decentralized workflow engine. So that's the two major technologies we leverage. And there's a bunch of other Uber-specific infrastructure technologies. I don't think that's worth to mention here.
네, 구체적인 얘기를 나누니까 정말 알차고 좋습니다. 또 궁금한 점 있으신 분 계실까요? 네, 오늘 마지막 세션이니까 마음껏 궁금한 점 있으시면 질문해 주시면 좋겠습니다. 네, 마이크 전달해 주시고요.
한국어로 하겠습니다. 아까 말씀하실 때 각 컨테이너별로 오버헤드가 많이 발생되는 현상이 있다고 했는데 그거를 좀 어떻게 해결을 하고 있는지 궁금합니다.
What the overhead of the container you mean here? Like what that means? Like overhead of container.
각 컨테이너별로 실제로 그 리소스가 할당된 것에 비해서 너무 사용률이 적게 각각 컨테이너별로 사용을 아까 한다고 됐었는데 그거를 어떻게 좀 해결을 하고 있는지 궁금합니다.
Yeah, what we mean there by comparing the cluster utilization versus the cluster allocation is essentially how Mesos works is Mesos provides offers to schedulers. So scheduler takes the offers and reserve that offers for certain tasks if it decided to place that task with that offer, which means, for example, you have a web service. You have a like a web server. You take the Mesos offer for, let's say, 8 cores and 10 gig of memories. Right? So essentially means all this resource on that specific agents enveloped in the Mesos offer are reserved for this specific web server instance. Right? But it doesn't really mean the web server instance is actually utilizing all this resources. It got allocated or reserved. So essentially means for critical services, for example, there are legitimate business use cases. You want to, for example, you want to over-provision your instances, your service to be able to handle or traffic spike. You want to over-provision the resources for your services to maybe handle the like failover use cases or scenarios. But on a daily basis, those resources are allocated to those services. But if they are not utilized by those services, they are sort of a waste for the entire platform. So the current situation in Uber Compute Platform is we essentially allocated a lot of resources, or majority of our available resources to the services, but there's only a low percentage of those allocated resources are actually being utilized by those services or containers running on the host. So that's the problem we refer to here. And unfortunately, as I mentioned, so we try to solve that problem by oversubscription, and we are still in the process of trying to co-locating batch workloads with stateless workloads, trying to solve that problem. But so far, we don't have a good solution for that.